All right, we're going to get on topic about temperature today. So if you don't want to be recorded, send me a chat, although I won't be able to see it because I'm in a different screen, but I'll see it at the end. So we're talking about temperature. Now, look at what temperature is defined as. It's the average kinetic energy of the atoms. So inside a container...
I can't see the screen.
Nobody can see it?
No one can see it.
Nope.
How unfortunate.
All right, let me get out of here and start the Zoom over again.
Third time's the charm.
Must have been all that recording. All right, now you can see it?
Yep.
All right, so inside the object, there's these atoms moving around. So there's like a gas in here in a closed container. So all these things are moving at their own unique velocity. So they can't all be moving the same velocity. So what we do is we average the kinetic energy, and the average of that kinetic energy is called the temperature. We measure it with a thermometer. So you guys are probably pretty familiar with a thermometer these days. And the three most common temperature scales are Fahrenheit, Celsius, and Kelvin scales. So we use Fahrenheit here in the United States, Celsius would be everywhere else, and then the Kelvin is the scientific scale. Does anybody know why we have a Kelvin scale?
So, because 0 is absolute 0.
Good, 0K, that's known as absolute 0. All right, so here's the temperature scale. This just shows you the relationship. Some important temperatures. Over here is absolute 0. Freezing point of water, you need to know this, especially on the Celsius scale is 0. And then the boiling point of water over here. And we're most concerned with Celsius and Kelvin. So we won't be using Fahrenheit very much. So 0 degrees Kelvin, 0 degrees Fahrenheit is freezing, 100 degrees is boiling. And then the conversion between Kelvin and Celsius, you have temperature Kelvin equals temperature Celsius plus 273 degrees. We'll just do 273, it's close enough, or 273.15. And then temperature Fahrenheit is equal to 9.5, not 9.5, 9/5 temperature Celsius plus 32. So those are your two conversion factors for temperature. Absolute 0 is the lowest temperature theoretically possible. It cannot be reached. It's impossible to reach absolute 0. You can't take all of the energy out because that would mean you violated the law of conservation of energy. So you can take a percentage of the energy out, but you can't take all of it out. So absolute 0 is impossible. There's no upper limit to temperature. Some stars are billions of degrees Celsius, so it's pretty hot. Now, heat is the flow of energy. Heat flows. So heat will flow until two objects have the same temperature, and that's known as thermal equilibrium. And heat always flows from hot to cold. Hot to cold. So here we have some cocoa. The heat is flowing out of the cocoa, or the hot chocolate, whatever you call it. And then over here we have some ice cream, and heat is flowing into the ice cream. So just an idea, in the winter, you open up the door in your house, you're not letting the cold air in, you're letting the hot air out. Just an easy way to remember that. When things heat up, what happens is the temperature goes up, and when the temperature goes up, the thermal or the kinetic energy goes up, because remember, temperature is the average kinetic energy. And remember, when you have more kinetic energy, you can do more work. So inside this hot air balloon, all these atoms are pushing outward. They're doing more work, and that's what causes the balloon to expand. So thermal expansion is the change in size of volume of a given mass with temperature. Now, if you have a refrigerator and you do the opposite, right? You open up the fridge and you stick a balloon in there, a helium balloon, let's say, you put that into the fridge and then you shut the fridge door. The helium balloon inside the fridge is going to shrivel up. because now you've slowed down the molecules. They no longer are pushing against the walls of the container and it shrinks. So that's the idea of thermal expansion. It has to do with the average kinetic energy and the work that these things can do. Remember, work is equal to force times distance. So they're pushing against the walls of the container. Here's just another example of thermal expansion. This is why we put joints, expansion joints and things. And you can see there's a lot of force. These railroad ties are moving because there was nowhere for the steel to go. So when it got hot, the steel expanded and it had nowhere to go. So it had to buckle. So that's what happened there. Water, liquids also expand. Water is an anomaly. Water is most dense at 4 degrees Celsius. So if it's most dense, that water at 4 degrees Celsius is going to sink to the bottom, right? We learned about buoyancy. The more dense you are, the less buoyant you are. So all the water at the bottom of the pond is 4 degrees Celsius. So that's why ice will form on the top of the pond and get lower and lower and lower. But this water on the bottom will still stay at 4 degrees Celsius because it's the most dense. So it sinks. So most objects or liquids do not have less density when they're frozen, but ice does. Ice is least dense when it's frozen. It's more dense when it's a liquid. And that's what this chart's showing you. It's showing you here, that's 4 degrees Celsius. It's the most dense. You can see here on either side of it that the density is going to be less, so the water is going to float. That's why in the summertime, you swim down to the bottom of the pond, it's cold, and the water above it is hot because the water above it is less dense. And this is important because then the fish and stuff can live on the bottom of the pond in the winter. It won't completely freeze over. All right, so the formula for thermal expansion, delta L equals, this is an alpha, Greek letter. I'll write it a little bit like that, like alpha L delta T. Now, alpha comes off of a chart. So this is on a chart. It's the coefficient of linear expansion, and I have the chart over here. Here's the chart. It's in your book if you need it for reference. Notice the units for alpha are 1 over Celsius. So alpha's units are 1 over degrees Celsius. All right, concrete highway slabs are poured in lengths of 10 meters. Gaps are left in the concrete to allow it to expand in extreme heat. Now what happens in the winter is water gets in those gaps and then the water expands, and that's what creates our potholes because ice is less dense, so ice is going to expand. So when the water in those gaps freeze, boom, that's how you get your potholes in your concrete and asphalt. But anyway, gaps are left in the concrete to allow it to expand in extreme heat. When the concrete is poured at 20 degrees C, how wide should the gaps be to ensure there'll be no contact between adjacent slabs over a temperature range of 20 degrees C to 50 degrees C? So our formula, delta L equals L naught alpha delta T. Right, there's our formula. This is L naught, that's your original length. So what we need is, we know that the original length is 10 meters. Delta T equals 50 minus 20. And we got to find alpha for concrete. We'll go to the next page here. 12 times 10 to the minus 6. So our goal is to find delta L. Delta L equals 10 times 12 times 10 to the minus 6 times 30. .6 times 10 to the minus third meters. which is 3.6 millimeters. So they're not super thick. That's all they'd have to be.
Where'd you get the 12 and the 10 to the minus?
On this chart. See it down there? You see it?
Yeah.
Any other questions here?
Seems pretty straightforward.
That is pretty straightforward. Yep. All right. Now, you may have noticed here this beta on this chart if you were looking. That is volume expansion. So you can see over here, if we're talking about a two-dimensional change, the formula is delta A, 2 alpha A, delta T. Three-dimensional change, right? So this would be two-dimensional. We're moving it out. This would be three-dimensional. So we're moving in every direction here. It's expanding. So it's 3 alpha. And 3 alpha is the same as beta. And we usually use this for volume expansion of liquids. So this is usually liquids and gases. So you could, the formula pretty much is the same, it's just tripled. And you use the volumes or the area instead of the linear. Any questions there? All right. Try this one.
So wait, we would need to look at that chart, right?
Yeah, you want me to get Copper's thing for you?
Yeah,
It is 17 times 10 to the minus 6.
17 times 10 minus 6, gotcha. I think I got A.
All right. Did you do B?
I'm not very
Remember,
sure.
it's pi r squared is the cross-sectional area.
Uh,
Well, you can just leave it in centimeters. Yeah, you can just leave it in centimeters. You don't have to change it to meters. So for part A, I got delta L is 0.204. So the new length is L naught plus delta L, 200.204 centimeters. And then B, delta A equals A 2A alpha delta T. My 2's and my alphas look a little alike there, but you got to figure it out. Delta A equals 2 times pi times 1.25 squared times 17 times minus 6 times 60. So 2. I got 0.01 centimeters squared. Anybody else get that?
Yep.
And
Good.
yep.
I did get, A kind of right. It's just I accidentally added the radius because I thought it was a length.
No, sorry.
Oh, okay.
Anybody else have anything they'd like to ask or add?
I got the 0.01, but where'd your 2 come into that equation?
That is the equation. 2 alpha, 2A alpha delta T. That's the equation for change in area.
Wait, what was the A?
A is the area. A is pi r squared.
Huh.
Anybody else? All right, let's move it on. Next, we're going to do the ideal gas laws. So we're just a little bit talking about liquids there and solids, liquids, and now we're going to talk about gases. 2 of the ideal gas laws, one is Boyle's law, the other is Charles' law. And then there's the ideal gas ratio. But Boyle's law tells us that the pressure times the volume is constant. That's what the K here stands for, is constant. So the pressure times the volume is constant. So in this case, the volume decreases, the pressure increases. Volume increases, pressure decreases. They're inversely. Ugh, that's so ugly. My writing is so ugly. It is spelled wrong. They're inversely proportional. It's ELY, inversely. One goes up, the other one goes down. I just did the same thing. And then Charles' law has a direct proportion. Temperature goes up, volume goes up. Temperature goes down, volume goes down. So this is telling us the volume divided by the temperature is constant. And the ideal gas ratio, P1 V1 over T1 equals P2 V2 over T2. So the amount of pressure times the volume divided by the temperature is always constant throughout the entire process. That's the ideal gas ratio. You have any questions there? All right. Moles. To do the ideal gas law, we have to understand the concept of a mole. A mole is the amount of substance that contains as many atoms or molecules in exactly 12 grams of carbon-12. So a mole is a quantity of matter. A mole is a quantity. It's how much. It's a way of classifying how much. And it's a really big number, right? This is something you should know. 1 mole of an ideal gas occupies 22.4 liters at STP. STP, that's standard, temperature, and pressure. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atm. And why I mention it, if it ever says room temperature, that's 68 degrees Fahrenheit or 20 degrees Celsius. That's room temperature. And remember, 1 atm equals 1.01 times 10 to the 5th pascals. Any questions on that?
That's 10 to the 5th.
Mm-hmm. That's, remember,
Okay.
where that's atmospheric pressure?
Yeah, I was just asking because I couldn't read your handwriting.
Oh, I'm sorry. Yeah. This pen wants to be thick today. 10 to the 5th. All right, let's try one. So we're just going to do a little bit of a mole thing. Now, to understand, when it says water, it says how many moles are in 40 grams of water? Well, water is made up of H2O. Now, you have to get out a periodic table. And there's one in the book. I should have one on this slide, but I just don't. So there's one in the book. I'm going to get one on the internet. I'll get one on the internet. Hold on. Hold on, team. Periodic table. Boom. So here's a periodic table. Let's just, oh, this one obviously doesn't have the masses on it because that would make my life too easy. Is this one? It's going to take me some crazy website. Oh my goodness, it's so hard to read. How did the world's worst periodic tables pop up when I typed in periodic table, may I ask? This one hasn't. All right. So you can see here on our periodic table, of course, everything's written in Russian, but it doesn't matter. We're just looking at the numbers here. This number right here at the top right, that's the atomic mass. That's how many grams per mole. So if you have a mole of carbon, it's 12 grams. If you have a mole of oxygen, it's 16 grams. Can you see that on the periodic table up here in the top right? So when we look at something like H2O, hydrogen is 1 gram per mole. And we have 2 of those, plus oxygen, which is 16 grams per mole. And we have 1 of those. So oxygen is 18, or water is 18 grams for every mole. So every mole of water weighs 18 grams. Now, if we have 40 grams of water, how many moles do we have? So we have 40 grams divided by 18 grams per mole. (2.22 grams, moles, sorry, moles. (2.22 moles). Now, if we do NO2, go back to our periodic table, nitrogen is 14, oxygen is 12. Uh-oh, what happened there? So we have 14 plus 2 times 16. Oxygen is 16, I meant. I said 12. I was looking at carbon. So that's 32 plus 14. That's 46 grams per mole divided by 138 grams. Wrong way, Mr. Manning. So we have 138 divided by 46. 3 moles of NO2. And then we'll go right to D. I think I skipped H2SO4, but that's fine. 56 liters of SO2. Well, remember, 1 mole of an ideal gas at STP is 22.4 moles. Or I'm losing my mind here. 22.4 liters. So this would be 56 divided by 22.4. 2.5 moles. So that's how you figure out how many moles you have from an equation. Any questions there?
I have a question.
Sure.
You know, never mind. It's gonna make me sound more dumb than I want to. Never mind.
Okay, no worries.
Guess I gotta buy a periodic table now.
No, there's one in the book. Or online. Just find one online like I did. On the test, I'll give you the moles. This is just an exercise for class and homework. I wouldn't make you look it up on the test, although I could. I don't see what the big deal is. Just look in your book. I'm sure there's one in there.
You just type in periodic table on Google Images, you'll get hundreds and hundreds.
Yeah, that's what I did. You saw I did that. Periodic, there's no one in your book. So you have to, there's one in there somewhere, I guarantee it. I just don't know where I write this second. All right, now. Oh, there's the formula. If you're looking for the actual formula. It is N, which is the symbol for the number of moles, that's N. So that's the symbol for number moles is an N. You just take your total mass and divide it by your formula mass. So this right here, this is our formula mass. That's how much mass this formula is. And then the total mass was the 138. All right. Now, Avogadro's number tells us, this says 1 mole always contains Avogadro's number of particles or atoms. So N, capital N, this is the number of molecules, equals N, number of moles, times Avogadro's number. So the number of molecules in a substance is equal to the number of moles times Avogadro's number. Big N equals little n times Na. So to convert between moles and molecules, you use Avogadro's number. That's what we need to remember here. Does that make sense? Has anybody ever taken chemistry and heard of this before, or is this all new?
I've heard of it.
Good.
Yeah, same.
So the relationship between molecules and moles is Avogadro's number. This 6.02 times 10 to the 23rd mole to the -1. So that's molecules or atoms per mole. That's what mole to the -1 means. So if we have an active pill is 325 milligrams, and it's CH9NO2. We want to find the number of molecules, big N equals. So carbon is 12 grams per mole. I'm just going to make a little chart here. Hydrogen is 1. Nitrogen is what? 14. And oxygen is 16. So you guys find out how many molecules we have in this Tylenol pill.
I think I got an answer.
All right, just hold tight.
Maybe.
So N equals 325 over 8 times 12 plus 9 times 1 plus 14 plus 2 times 16. So N equals,
I have a question.
yeah,
Where did you get the subscript for those? Like the 8 times 12. Where'd you get the 12 from?
where's 12? 12 is the mass of carbon.
Oh,
And
so I
there's
need to
8 of
figure
them
out
in
a
the
table for
formula.
that. Okay.
There's 8 of them in the formula. So I got N to equal 2.15 moles. So then big N equals 2.15 times 6.02 times 10 to the 23rd. N equals, oh man, 1.30 times 10 to the 24th. Ken, is that what you got?
No, not even close.
Did
Yeah.
anybody get that? Is that not right?
Yeah, my calculator spit out the wrong number. I need to give it some spacing so it does it correctly because my calculator's dumb.
I don't think it is. Yeah, I got the same number twice.
There we go. Now it works.
Get
Yeah.
it?
I got that.
Good.
Yeah.
Good. All right, so let's move on to the next one. Everybody got it? Any questions there before I move on? So the ideal gas law comes in two things, microscopic and macroscopic. Microscopic uses the number of molecules because that is really small, right? To the 23rd power, there's a lot of molecules in there. So the ideal gas law gives us a relationship between the number of molecules Hey, can you turn your AirPods off? I don't know. Can you guys hear me still?
Yeah.
Yeah.
All right. When you talk in your AirPods, they might be able to hear you. It just came up on my screen. I guess I could shut my Wi-Fi off, but that wouldn't help. Where was I? The number of molecules is very small. So this is a relationship. So if we have a container, right, and we have all these molecules in this container and they're moving around. Remember we talked in the beginning? Those are really bad molecules. But anyway, they're all moving around in there. So the number of molecules, the temperature, the pressure, and the volume are all related to each other. How fast they're moving, how much pressure is in there, how hot it is, and the volume, all related. And they're all summed together with this Boltzmann's constant, 1.38 times 10 to the minus 23rd. Joules per Kelvin. Joules per Kelvin. So notice this temperature is in what format? Great job, class. That's in Kelvin. So that means when you solve for temperature up here, you've got to convert it to Kelvin. You have to convert to Kelvin in the ideal gas law. It has to be in Kelvin. Joules. Joules are made up of kilogram meter per second squared times a meter. So pressure has to be in newtons per meter or pascals. Volume has to be in cubic meters. So you got to make sure you convert those. Because this is a Newton meter, right? A joule is a Newton meter, so a Newton over a meter. Excuse me. Yeah. So anyway, make sure you do that. Oh, this is newtons per meter square. That's where I was getting screwed up. So make sure you convert when you're doing the ideal gas law. For both microscopic and macroscopic, you have to convert to SI units. And I said it right here too. Questions there? All right, let's try one. A person's lung capacity is 6.5 liters. Well, that's a volume. Assuming air to be an ideal gas, how many molecules of air are in their lungs? So we're looking for how many molecules when the air temperature is 38.5 degrees Celsius under normal atmospheric pressure. So pressure is 1 atm. Oh, major conversions are going to be taking place here in a moment. So we need to know the meters cubed, right? There's 1,000 liters in 1 cubic meter. (6.5 times 10 to the minus third meters cubed). We have Celsius here. So we're going to add 273 to get Kelvin. Can I do this in my head? I don't think my brain is working that strongly today. 311.5. And 1 atm is 1.01 times 10 to the 5th pascals. We know that. PV equals N kBT. So that means N equals PV over kBT. Remember what KB is 1.38 times 10 to the minus 23rd? So now we can just plug in. I got 1.59 times 10 to the 23rd. Anybody else get that?
Once you get the units right, it's not too crazy.
Not it's just as long as you can put it in your calculator, you know, with the
Yeah.
exponents, that can throw you off. Anybody have anything that need clarified there?
Can you just stay on this page for a bit? I'm still trying to write this down.
Sure.
There's no way I'm getting this test question right.
Have patience, grasshopper.
Oh, my mic was still on. I finished writing everything down.
All right, thanks. Anybody else? Now, on a macroscopic, so this is on real world size, things you can see with your naked eye. PV equals nRT, where R is the ideal gas constant, 8.31. This is the ideal gas constant. Joules per mole Kelvin. And again, T, V, and P all have to be converted, but this is the ideal gas constant, R, and it's the same formula except we're using R now. Ready? This one you guys get to do. How many of these do I got? One. Try this one at your seats.
Sorry, what did R equal again? Is it 8.31?
I got that backwards. I knew I had it backwards. Yeah, 8.31.
So what exactly was lowercase n again? Was that another constant?
No, that's the number of moles. So
Oh,
in this
yeah.
case,
Thank you.
n equals 15 moles. (92.84 degrees Kelvin, or just Kelvin? It's not degrees Kelvin. 92.84 Kelvin. How do we do?
I just need to remember to convert the volume and the atmosphere. Right.
Yeah, that's the killer. Anybody else?
So wait, when we run it through, the equation right there for T, would it come out as Kelvin or will we have to convert it?
Yeah, because R is joules per mole Kelvin. So when you do, right, that's joules per mole Kelvin. So when you do this math, right, this is moles, blah, blah, blah. The mole Kelvin's on the bottom. Right, they cancel, those would cancel, and you'd be left with Kelvin. Does that make sense?
Yes.
So for the conversion for P, the pressure, what you wrote down doesn't really make that much sense. Is that supposed to be like 14 equals, or is it like 14
No, that was just a
times?
line. Remember, 1 ATM is 0.1 times 10 to the 5th pascals. So 14 ATM, 1 ATM, 1.01 times 10 to the 5th pascals. That's how you convert it.
Wouldn't this temperature depend on what the temperature was before?
This is the temperature for these settings with the volume and the pressure, right? If they were to change, then you'd have a change in temperature. This is just the temperature for this exact situation, what the temperature of the mixture would be.
And temperature is different than heat, right?
Temperature is different than heat. Heat temperature you can have, heat you give. We'll talk about heat soon enough. Any other questions? All right, we'll probably hop right along to our quiz then. If you're ready. This is a homework. This is a question out of the book you can do if you want. All right, give this a try.
Is this the quiz?
Quiz, yep.
All right.
You can leave your answer in gallons. I'll give you a hint. Everybody ready for me to, you have your information down? Can I flip over?
Keep it up for one more second.
So, did I get wrong?
I don't know, Ken. I can't see it yet. Remember, I have to wait till everybody's done copying the information down.
Oh,
Did you send your answer just to me or to everybody?
just to you.
Everybody got it?
You go back to that page where it says this formula, like the one with beta in it.
The beta formula?
Yeah, I just realized I wrote the alpha and not the beta.
I'll give you a hint. How's that?
Sure.
How's that? Does that hint help?
Yep.
All right, I'm going out of here. Going back to the old Zoom.